Artificial intelligence is a hot topic nowadays. People see it as another technological revolution after the Industrial Revolution. Some even argue that the impact of artificial intelligence on humanity far exceeds that of the Industrial Revolution because it involves and changes more fundamental ethical and philosophical propositions. In the upcoming video episodes, we will explore the historical evolution of artificial intelligence, various achievements in the current hottest fields of machine learning and deep learning. Then, we will open up our imaginations and discuss, irresponsibly, the future of artificial intelligence and the various issues it may trigger. Today's topic is a brief history of artificial intelligence, its past and present. Before delving into this topic, let's first discuss intelligence. Intelligence encompasses various domains and competencies such as abstraction, logic, understanding, self-awareness, learning, emotions, reasoning, planning, creativity, critical thinking, and problem-solving abilities, among others. It can be described as the ability to perceive or infer information, retain it as knowledge, and apply it adaptively in the environment or context. Humans have gained a lot of specific insights into intelligence or cognitive abilities, but a consensus has yet to be reached because it involves profound philosophical questions, leading to ongoing debates among people. It should be noted that many forms of intelligence are not unique to humans or animals. Some people even suspect that all human intelligence is also exhibited in other animals and plants. Those who like to argue may ask me to provide some examples. We know that primates, various pets, and birds, such as parrots, demonstrate considerable intelligence. Regarding the intelligence of plants and fungi, I will give some examples here. Firstly, many plants have short-term memory. For example, the Venus flytrap has numerous trigger hairs on its leaves. If 2 of these trigger hairs are touched by an object within approximately 20 seconds, the leaf will close. After capturing prey, the Venus flytrap starts secreting digestive fluids after the trigger hairs are touched 5 times. Plants also exhibit long-term memory. Mimosa pudica can remember harmless stimuli to avoid unnecessary energy expenditure in the future. Plants are capable of solving various problems encountered in their growth environment, sometimes even better than humans. For instance, plants can determine their growth direction based on the direction of sunlight, and they form their root systems based on the distribution of moisture and nutrients in the soil, thereby enhancing absorption. Plants also communicate. Some plants exchange environmental information, such as about pests, through the secretion, transmission, and absorption of chemical substances. Regarding intelligence, I haven't found a perfect, universally accepted definition. If you are very interested in this, you can read the book Frames of Mind. The author is Howard Gardner, a professor at the Harvard Graduate School of Education. Fortunately, for the artificial intelligence we are discussing, it currently only involves very simple aspects, and people have a relatively consistent understanding of these aspects, including logic, reasoning, planning, abstraction, etc. Many people may think that current artificial intelligence already possesses creativity, such as drawing, writing poetry, writing, composing music, but I hold a contrary opinion on this. I will discuss my views on this in future videos. Let's now delve into the concept of artificial intelligence. Nowadays, many people equate deep learning, neural networks, and the like with artificial intelligence. This actually undermines the dreams, research efforts, and various achievements of many predecessors. Without these contributions, we wouldn't have the deep learning and neural networks we have today. According to Wikipedia, artificial intelligence refers to the intelligence of machines or software, not the intelligence of humans or other animals. I have a somewhat different perspective on this. My definition is that artificial intelligence is the creation of artifacts derived from the general principles deduced by humans in the study of the essence of intelligence. These artifacts, to some extent, achieve a level of intelligence recognized by humans. This is a more general definition. Under this definition, regular computers and some ordinary non-deep learning based software are also a form of artificial intelligence because they can perform various high-level intelligent tasks, such as organizing data, conducting computations, making decisions, and manipulating machinery. I understand that enthusiastic viewers may feel somewhat disappointed with this definition, so let me refine it further. These artifacts achieve a certain level of human-recognized humanoid intelligence. This intelligence encompasses semantic understanding, visual recognition, sound recognition, including speech, emotional recognition, and other forms of intelligence that are difficult to process and simulate using simple, structured, formalized, or programmatic approaches. Regarding this definition, I would like to add a few points. Firstly, all the artificial intelligence we currently implement is achieved through mechanical or electronic means, primarily based on electronic computers as platforms. However, in future research, various forms of intelligence using other forms and carriers may emerge, such as biological, chemical, crystalline, quantum, and so on. Especially, I see direct construction of brain-like structures in biological forms as a very promising approach. Secondly, we need to exclude artificial biological life forms. Here are two somewhat speculative examples. One is the creation of intelligent species through genetic manipulation. This kind of artificial life is essentially a byproduct of human manipulation of genes, rather than something created by humans based on a comprehensive understanding of the mechanisms of intelligence according to universal intelligence theories. Another example involves selectively cultivating the brains of certain animals to achieve partial human-like intelligence. Defining this example can be challenging. If humans happen to discover this method and utilize it without understanding its mechanisms, then it falls under biological intelligence rather than artificial intelligence. However, if humans fully comprehend the principles of biological neural networks and use them to selectively cultivate animal brains, I consider it artificial intelligence. The reason people might not create from scratch could be merely due to the cost-effectiveness of this approach. Now, let's move on to the main topic of this episode, the history of artificial intelligence. Human dreams of artificial intelligence began with ancient myths and legends. In Greek mythology, there were golden automatons created by the god of fire. Many ancient civilizations had craftsmen who created automatons, such as the Yanshi in western Zhou, China, and Heron in ancient Greece. In 19th century science fiction novels, artificial beings and machines capable of thought had already appeared. Even today, artificial intelligence and robots remain popular themes and indispensable elements in science fiction literature. When it comes to artificial intelligence, one cannot avoid the discipline that deals with the laws of thought, logic. Logic is almost as ancient as humanity's dreams of artificial intelligence and is closely related to the development of AI. Logic studies the laws of human thinking. If we can summarize the laws of thought, formalize them, and implement them in some device, wouldn't that achieve artificial intelligence? This approach is one of the earliest and most crucial directions in the field of artificial intelligence. In its modern sense, logic initially belonged to the realm of Western philosophy, originating from the study and induction of the thought processes of ancient philosophers. The outcomes of these studies constitute traditional logic. It wasn't until the recent and modern era that logic separated from Western philosophy and became a branch of mathematics. The germination of logic was found in ancient Egypt and Babylon. Ancient Greece, India, and China independently developed logic and, in the first millennium BC, developed structured formal deductive methods. The logic we use today originated in ancient Greece and philosophers in medieval Europe and Islamic philosophers also made contributions to logic. The culmination of ancient Greek logic is formal logic and formal reasoning, also known as mechanical reasoning. Their ideas are prominently reflected in Aristotle's logic, Euclid's Elements of Geometry, and Khwarizmi's The Compendious Book on Calculation by Completion and Balancing, often referred to as algebra. Aristotle is the synthesizer of classical Western traditional logic and the forerunner of modern logic. Traditional logic, also known as term logic, was formulated by Aristotle. He inductively summarized some universal laws of thought and expressed them in a formalized, mechanized manner. One of the most well-known aspects is probably the syllogism. Euclid's Elements of Geometry established and applied the model of formal reasoning, and these formal reasoning methods were further established and developed in Al-Khwarizmi's algebra. In the medieval period, the Moluccan philosopher Raman Lull attempted to develop logical machines that could generate all possible knowledge by combining basic undeniable truths through simple, mechanical logical operations. This was a tremendously imaginative and admirable idea. Personally, I believe Raman Lull's logical machines serve as prototypes for modern expert systems. Given the technological constraints of his time, realizing such machines was undoubtedly impossible. However, his ideas had a profound impact on later thinkers, including Gottfried Wilhelm Leibniz. In the 17th century, Leibniz, along with thinkers like Thomas Hobbes and René Descartes, sought to transform systems of rational thought into structures akin to algebra or geometry. Hobbes indeed had a famous quote in his work Leviathan: "Reason is nothing but reckoning." Leibniz envisioned a universal language for reasoning that could reduce philosophical arguments to calculations, making it so that philosophers, just like accountants, no longer need to argue, but only need to calculate. This explicitly introduced the hypothesis of formal symbol systems, which later became a crucial guiding principle and research direction in AI studies. Sidebar: Descartes' methodology provided Western scientific research with a clear, concise, and implementable approach. These methods propelled the rapid development of Western modern science and have also been directly applied to the field of artificial intelligence. If you take a closer look at the research during this period, you'll find that the pursuits and imaginations of these geniuses, even by modern standards, often surpass the endeavors of the majority of ordinary scientists. Logic experienced a revival in the mid-19th century and evolved into a rigorous and formal branch of mathematics with a new perspective. During this period, figures like Boole, Frege, Russell, and Peano founded and developed modern symbolic or mathematical logic, now referred to as mathematical logic, symbolic logic, or logic algebra. Mathematical logic sits at the intersection of mathematics and philosophical logic, focusing on the portion of classical or philosophical logic that can be formalized in mathematical terms, also known as metamathematics. Mathematical logic typically emphasizes the study of the inferential and expressive capabilities of axiom systems, with its objects of study being the formal systems resulting from the symbolic representation of the intuitive concepts of proof and computation. It is an indispensable component of the foundation of mathematics. Mathematical logic has developed into a vast discipline with numerous subfields, forming the theoretical basis for artificial intelligence. Mathematical logic and computer science, especially theoretical computer science, share many commonalities. Many pioneers in computer science were both mathematicians and logicians, such as Gödel, Alan Turing, Alonzo Church, Claude Shannon, Stephen Cole Klein, and others. Many of them also played pioneering roles in the contemporary field of artificial intelligence. During this period, there were abundant research achievements, and we will focus on introducing the parts that had a significant impact on computer science and artificial intelligence. The breakthroughs in mathematical logic seem to herald the emergence of artificial intelligence. Building on the research of George Boole and Gottlob Frege, Bertrand Russell, along with his teacher Alfred North Whitehead, provided a formal description of the foundations of mathematics in their co-authored work Principia Mathematica. This achievement inspired David Hilbert, who posed a foundational challenge to mathematicians in the 1920s and 30s. Can all mathematical reasoning be formalized? The ultimate answer to this question came from Gödel's incompleteness theorems, Turing machines, and Alonzo Church's lambda calculus. Their answers were astonishing. Firstly, they proved the limitations of mathematical logic, essentially stating that in this universe, there is no perfect mathematics or theoretical system, and we can always construct paradoxes to refute any theory. Secondly, and more crucial for A, their work implied the possibility of mechanizing any form of mathematical reasoning within these limitations. In other words, theoretically, we could create machines operating according to these theories to achieve artificial intelligence. The Church-Turing thesis suggested that a mechanical device capable of handling simple binary symbols, such as 0 and 1, could simulate any mathematical reasoning process. The key inspiration here was the Turing machine, a seemingly simple theoretical construct that grasped the essence of abstract symbol processing. This creation sparked scientists' exploration of the possibility of making machines think. As mathematical logic advanced, the legendary tale of computer science gradually unfolded, and artificial intelligence almost developed in sync with contemporary computer science. Now let's review this fascinating history. The gestation period of modern artificial intelligence occurred in the 1940s and 1950s. Prior to this, a series of mathematical, scientific, and engineering advances hinted at the possibility of constructing electronic digital brains. It's worth noting that, in the 1950s, there were attempts to use analog circuits for robots. Let's take a look at some crucial discoveries and advancements that played a vital role in the birth of artificial intelligence during this period. Neurological studies discovered that the brain is composed of a network of neurons, and their excitation levels exist in only two states, on and off, without intermediate states. Norbert Weiner's cybernetics described the control and stability of electronic networks. Claude Shannon's information theory explained methods for expressing and processing information using digital signals on or off. Alan Turing's theory of computation demonstrated that any form of computation can be described in a digital manner. Turing may have been one of the earliest thinkers regarding artificial intelligence in the modern sense. In 1943, Walter Pitts and Warren McCulloch analyzed idealized artificial neural networks and demonstrated how they could perform simple logical functions. This was the first clear description of artificial electronic neural networks. Inspired by Pitts and McCulloch, the young Marvin Minsky, in collaboration with Dean Edmonds in 1951, built the first neural network machine called SNARK. Minsky later became one of the most significant leaders and innovators in the field of artificial intelligence. In 1950, Turing published an influential paper titled Computing Machinery and Intelligence, in which he envisioned a possibility that humans could create machines with genuine intelligence. Due to the lack of a clear definition of intelligence at that time, he wisely sidestepped the issue and proposed the famous Turing test. It's essential to note that the Turing test is not a strictly scientific test, but a philosophical one. Given the technological constraints of the time, his test was as follows. If a machine could engage in a conversation with a human via teleprinter in a way indistinguishable from a human, it could reasonably be said that the machine was thinking. This simplified version of the problem allowed Turing to convincingly argue that a thinking machine was at least plausible, addressing all of the most common objections to this proposition in the paper. Indeed, the Turing test, while deceptively simple, strikes at the essence of intelligence. It avoids endless debates and clearly points out the direction of research. Great scientific figures often possess the magical ability to simplify complexity. In 1951, Christopher Strachey developed a checkers program using the Ferranti Mark I computer at the University of Manchester. Dietrich Prinz also created a chess program. Arthur Samuel's chess program, developed in the mid-1950s to early 1960s, demonstrated sufficient strength to challenge skilled amateur players. Game AI has long been considered a standard for evaluating progress in AI. In the mid-1950s, as digital computers became feasible, some scientists instinctively realized that machines manipulating numbers could also manipulate symbols, and symbol manipulation was likely at the core of human thought. This marked a different approach from neural networks in creating thinking machines. In 1955, Alan Newell and later Nobel laureate Herbert Simon, with the assistance of J.C. Shaw, developed the logic theorist program. This program could prove 38 out of the first 52 theorems in Principia Mathematica, with some proofs being more novel and elegant than those in the original work. Simon believed they had solved the mystery of the mind-body problem and explained how a system composed of matter can have the properties of mind, a philosophical position later referred to as strong artificial intelligence, suggesting that machines could have thought similar to humans. History finally arrives at the crucial year of 1956 when John McCarthy, Marvin Minsky, Nathaniel Rochester, Claude Shannon, and others initiated the Dartmouth Artificial Intelligence Summer Research Project workshop. The goal was to gather like-minded individuals to discuss artificial intelligence. The term artificial intelligence itself was officially coined by John McCarthy during this workshop, marking a key event in the formal birth of artificial intelligence as a discipline. The conference lasted for 6 to 8 weeks and was essentially a brainstorming session. On September 2, 1955, the four of them submitted a proposal seeking funding for the project. Here are some excerpts from the proposal. We propose that a 2-month, 10-man study of artificial intelligence be carried out during the summer of 1956 at Dartmouth College in Hanover, New Hampshire. The study is to proceed on the basis of the conjecture that every aspect of learning or any other feature of intelligence can in principle be so precisely described that a machine can be made to simulate it. An attempt will be made to find how to make machines use language, form abstractions and concepts, solve kinds of problems now reserved for humans, and improve themselves. We think that a significant advance can be made in one or more of these problems if a carefully selected group of scientists work on it together for a summer. They mentioned that they would discuss computers, natural language processing, neural networks, computational theory, abstraction, and creativity. The Dartmouth conference had over 20 participants, and most of them did not stay involved for long. No papers related to AI progress were published, and they engaged in a lot of general discussions. Some discussions were without a clear purpose, while others were encouraged by the organizers, such as discussions on symbol systems, early expert systems, and mimetic domains, deductive and inductive systems, and more. It can be observed that their greater interest lay in how to integrate future mathematical theories and technological discoveries to achieve artificial intelligence. Many of them became advocates and key figures in the field of artificial intelligence in the years following the conference,